New solution of Fibonacci's problem. The history of problem. The name of the Italian mathematician Leonardo Pisano is well known. He is also called the Fibonacci, that means the son of Fibonacci. From his main works, two books must be mentioned: Libera Labaci and Practica Geometria. The first book contained reference of arithmetics and algebra known by that time, and the second book is the usage of algebra in geometry. Both of these books remained as table books for mathematicians for more than 2 centuries. His name was given to a well-known sequence, where the next number is the sum of the previous one. Properties of Fibonacci sequence were discussed in many books. Many articles were dedicated to these properties, but Fibonacci sequence is not related to our project. The purpose of our project is to generalize the problem of congruent number. According to old traditions, Fibonacci participated in different mathematical competitions. His name has spread widely. In 1225, Emperor of Rome, Frederick II, with his mathematicians arrived in Pisa to test him. The problem was the following: find a number which is perfect square, and if we add or subtract 5 from it, we still get a perfect square. This problem was posed by the mathematicians Theodore and Joan de Palermo. Fibonacci found the number is the rational number. We don't know how Fibonacci managed to solve this problem, but he did it perfectly. In reference MacLennan, Leonardo of Pisa and his Liberal Quadratorum, and Popov's historical problems, we see the following solutions. Possibly Fibonacci solved the problem in this way, but how did he guess to substitute 10 by 80 multiplied by 18 divided by 12 square fraction? This guess seems surprising and impossible. After generalization this problem for arbitrary, we get so-called congruent problems. Find a square number x is equal to x squared divided by y squared, such that when a given integer r is added or subtracted, new square numbers are obtained. Such r are said to be congruent because r is common difference of a 3-term arithmetic progression of squares. Congruent problem has some interpretation.
Known results about congruent problem. For a positive integer r is a congruent number. There exists a rational number x such that x minus r, x and x plus r all are rational squares. There exists a rational right triangle with area r. There exist positive integers k, m and n, so that k in second power r equals m multiplied on n and multiplied on m in second power minus n in second power. The curve y in second power equals to x in second power minus r in second power multiplied on x as rational point. Knowing in advance if a number is congruent or not is a difficult problem. Just a few conditions are known. First, Fibonacci proved that a congruum must be divisible by 24. He also proved that a square cannot be a congruum. The only square-free congruent number less than 100 are. The smallest congruent number is 5. A prime of the form 8k plus 3 is never a congruent number. A 2p number with p equals 8k plus 5 prime is never a congruent number. A number pq with p and q primes of the form 8k plus 3 is not a congruent. A number 2pq with p and q primes of the form p equals 8k plus 5 is not congruent. There are 361 square-free congruent numbers less than 100. If positive integer is one of the form 8k plus 5 plus 6 and plus 7, then it is conjectured to be congruent.
Our research. In preceding paragraph, we introduce known results about congruent problem. In this paragraph, we will give new equivalent definition which we have not seen before. By using this new property, we will prove if congruent problem has for given R even one solution. It has infinitely many solutions, and we will obtain resource relation how to get new solutions. Theorem: if congruent problem seen below has solution, there exists three-term arithmetic progression A1, A2, and A3 with common difference D, so that A1, A2, A3 is equal to dRy square. And we seek congruent problem solutions by the form x is equal to x squared divided by y squared. We have two equalities. By the problem condition, x plus ry square and x squared minus ry square are perfect squares, so exists numbers n and m, so that we will get these two equalities. After addition, we have these two qualities, and we will get a third formula. If we substitute this in first or in second, we will get following. Of course, m must be more than n, and numbers n plus m divided by 2 and m form arithmetic progression with common difference d, which is equal to m minus n divided by 2. We prove the theorem. This theorem gives us the possibilities to construct new solution of congruent problem if one solution is known. Let's consider Fibonacci's solution. Of course, these solutions themselves form the arithmetic progression with difference 5, so we can use them for A1, A2, and A3. Now let's take n and m. Because d is equal to r, value of y will be rational by the following. By using the third formula, we will get x following. And after calculation, performing division x by y, x is equal to x squared divided by here. We get x following. New solution of Fibonacci's problem is this number. The direct calculation proves that this is second solution of tournament problem. You see it here. So we construct new solution by using known one. Now this encourages us to obtain resource formula for congruent problem solutions. Let's denote known solution by xn and new one by xn plus 1. We have these two followings. By using above described method, we have yn plus 1 and xn plus 1. After division, we get new solutions, which you can see on the next pages. After division by numerator and denominator by yn in fourth power, we get following. By using our recurrence formula, we can find another solutions. Now, let's shortly summarize results of this paragraph. If xn is equal to xn divided by yn and in second power is solution for congruent problem for given r, then new solution for the same r will be following. In another notations, xn plus 1 is equal to xn squared plus r squared in second power divided by 4xn multiplied by xn squared minus r squared. Conclusion. In 13th century, Fibonacci solved the following problem. Find a square number which being increased or diminished by 5 gives a square number. Fibonacci's solution is 41 divided by 12 in second power. In our project, we found general method of finding other solutions. For example, our solution of given problem is this number.